All right, everyone, I guess we'll get started. I want to welcome everyone to today's session. We're going to be talking about failure mode effects and criticality analysis and highlighting some of the capabilities around failure codes within EAM as well. I am your presenter. My name is Daniel LaFurla. I co-manage the EAM pre-sales team at HxGN. What is a pre-sales team and what do I do? Well, we take your requirements and map them to the solution, normally through demonstrations as part of the engagement process, but we also answer questions, we help with enablement, we have deep knowledge of the product. So that's why I'm up here, to help train and get you advanced in your maintenance maturity level. A little bit of history about myself. I've been working with enterprise asset management solutions for close to 20 years. Started implementing asset management solutions. I was a technical solution architect working with the EAM product for many years before I joined the sales team, and here I am. I've worked in a number of different industries. I've worked with naval facilities implementations that are millions of dollars to small frozen food packaging plants in the middle of Texas. So anything and everything, I can probably talk to you about it. So as we go through this presentation, we will be holding questions generally till the end. We recommend using the Streamline app. Submit your questions there. We'll provide time at the end to answer them. If you have a burning question that you absolutely have to ask, or you'll forget it, I'll take it. So feel free to raise your hands, but we'd like to hold the questions to the end and utilize the Streamline app, the CVent app, whenever we can. Okay? So let's get started. When we're talking about failure codes and failure mode effect analysis, we're going to be educating you on how you can implement some of the topics that George was discussing that you've heard throughout the presentations the past day and into today. So we're going to start by first understanding failures. We'll talk about why failures occur and how they relate to reliability-centered maintenance. We'll look at capturing those failures. We'll look at what closing codes you can grab in EAM, how to make it easier to capture those closing codes, what you can do with those closing codes from mean time between failure to reliability curves, similar to what you've seen in George's presentation yesterday. Then we'll look at failure mode effect and criticality analysis. We'll discuss how you identify failure modes, how you apply it to equipment, and ultimately how you can mitigate the risk of failure by implementing specific strategies to those pieces of equipment. But I'd like to start today about talking about odds. And I apologize to any of my Eagles fans in here if this image causes any angst. But I was curious, and this is a rhetorical question, you'll have to answer it. If you had to guess, how many professional sports bettors would you say succeed in the long run? Some people might say 10, some people might say 8. The average is between 3 to 5%. Now, that means that the Vegas odds makers win a staggering 95 to 97% of the time. Now, if you were looking at mitigating the risk betting against odds makers like this, would you even take this kind of bet? I don't think in the long run you would, because there would be a 97% chance of failure. But this actually poses a unique situation that we could use to describe why understanding the risk and mitigating the failures is important from a probability perspective. Because this means that Vegas is very successful simply by the fact that they look at the historical data and then analyze through their models to determine what the probability of success is, and they've gotten very good at it. So what's your probability? Let's say you have a pump. This pump is increasing in temperature or vibration. What would the risk of failure be? Would it be 6%? Would it be 12%? I mean, those are pretty high numbers. And what would you do in the event of a failure at that stage? Would you increase your maintenance efforts? So when we look at historically what to do based on the probability of a failure, you want to take action on those items that you know, the past successes that you've had, to try and beat the game the way that the Vegas odds makers do. So we'll look at how you can identify probability based on the potential of failure, or how you can hedge your bets and mitigate failures using that probability. But in order to get into the conversation, I want to discuss briefly maintenance maturity. Yesterday, George talked about the move to Industry 4.0 and ultimately Industry 5.0. We also look at this as an increase in maintenance maturity. And you may see some of these topics with the presentation of Kevin and Javier later today. But when we're talking about maintenance maturity, it aligns directly with the industry model as well. Maintenance 1.0 is CMMS, where you're constantly reactive, running to failure, you're battling this downtime, and then something is fixed. When you're into maintenance 2.0, that's generally handled by a CMMS and an EAM solution, where you're utilizing preventive maintenance on a predetermined schedule. What we like to move into is maintenance 3.0. A lot of people that we see are between 1 and 2, high 2s moving into 3 as well. So don't let this scare you if you're not anywhere near 4, because I don't really know very many people that are near 4. Even the biggest organizations are having a difficult time getting to 4 and beyond it. When we look at what we can do to increase our maintenance maturity, we look at maintenance 3.0, which is utilizing condition-based maintenance. This is where reliability-centered maintenance comes in, and this is where predictive maintenance comes in. It can be based on sensor data, it could be based on inspection readings, it could be based on a number of different things. But this is the area where a lot are striving to go. And if you're trying to increase your maintenance maturity, the first step is going to be looking at how you could get to asset performance management. So there are some components, and we'll talk about that as well. The final one that we're looking at here is maintenance 4.0. This is predictive maintenance. This is algorithms, machine learning, highlighting the probability. This is where you build on some of the topics we talk about today and utilize those advanced algorithms to ultimately have the highest probability of success in avoiding failures. So let's look briefly about some reliability-focused strategies. When we talk about reliability-centered maintenance, there's a couple of strategies here, and they'll all play into the next slide too. When we look at asset strategy for risk management, you're looking for tools to calculate risk. You're looking for tools to assess the criticality, understand mechanical integrity, and have a library of failure modes and recommended practices. Reliability-centered maintenance takes that a little bit further, where you look at failure mode affecting criticality analysis by using those failure modes to identify the criticality of assets and the ultimate risk that's associated to them. So we'll dive into that too. There's also condition-based maintenance. This is where you're utilizing rules engines and determining record tolerances of data that's coming in based on the asset itself, and then ultimately triggering work and execution based off of those readings. Then there's predictive maintenance. This is on this slide talking about Monte Carlo analysis and statistical analysis and neural networks and machine learning, but predictive maintenance can also include some of the topics we'll discuss today from a reliability-centered maintenance perspective. So what does this do? We are trying to move on that maintenance maturity curve from a 1 to a 2 to a 3 and ultimately to a 4. And in order to do that, you need to evolve from EAM to APM. When we talk about asset performance management, it's the understanding of risk, criticality, and condition in order to prioritize the maintenance of the highest priority assets, those that are potentially poor condition or high risk. So when we're looking at what we can do with failure modes, we'll talk about it from the perspective of trying to advance into asset performance management. And this will be a common theme for any of the sessions I'm doing today. There's a couple more that are going to be this afternoon. Now let's get really into it. We talk a little bit about why failures occur. Anyone here has experienced a failure, I'm sure. But when we look at some of the failure options and how we can track that, we look at improper operation. So operators themselves, either through lack of training or a lapse in judgment, or they're just sleepy from the night before, they can have an impact on equipment, and that can ultimately result in a failure. Preventive maintenance can result in failures. If you're over-maintaining an asset or under-maintaining an asset, it could reduce the useful life of that asset, ultimately respond with a failure. Manufacturer defects are common amongst assets as well. So your equipment could fail simply because there was a problem in the manufacturing of it. So you want to try and identify that so that you can get ahead of those issues as well across like assets. Then of course there's aging equipment. So if you remember the curve that George was talking about yesterday, there's infant mortality where assets fail immediately, and then there's ones that reach the end of their useful life where they're failing at the end. So the ones that fail more towards the end, those are going to be your more, you're less probable to fail and actually more significantly or easier to maintain assets. Excuse me. So let's dive into predicting failures and talking about failure modes and failure codes. So we're going to look at common codes and how standardizing them is important, but we need to note a difference that we're going to talk about. There's failure codes. These are the closing codes in EAM. This includes common language, which is very important for reporting. You want to have a standardized set of closing codes so that way you can refer back to any closing action or any failure action and understand exactly what happened regardless of what comments were put in or any history of the asset. Those codes themselves will result in proper reporting and can utilize some of the tools in EAM to help you predict those failures in the future. They relate to specific actions. So, this pump is leaking, this pump, what's the problem and what's the code or cause of it. We talked about the standardized pieces, but there's additional failure codes that are listed in the system. You're probably very familiar with problem, failure, cause, and action. Those are the four that are the primary ones if you're utilizing closing codes in EAM. But there's also symptoms. So as you start to identify symptoms of assets, this could be a pump is leaking hydraulic fluid. You don't necessarily know why, you don't necessarily know what problem it's causing or what the failure is going to be, but that's a symptom that's related to some of the causes. There's also human factor. So the pump is pumping, or the operator pushes maybe the wrong button and causes a failure. There's human oversight, where maybe you failed to adjust the process and you're pumping too much liquid through the pump, overloading it causing it to fail. There's also workmanship issues, where if you've refurbished it recently in-house, potentially somebody did not refurbish it properly, and that's causing it to fail. And of course, there's tactical, where it might be pumping the wrong fluid and there's areas that you need to adjust. Then we look at failure modes. These are the functional failures, and this is going to be the crux of the topic that we're going to discuss today when it comes to failure mode effect analysis. You want to understand what the function of an asset is if this pump is pumping liquid, what the functional failures are if it's potentially leaking, what the probability of those failures are, if it's 20% or if it happens every year, what the risk calculation is. And this is where we get into the impacts and the effects of them. So if one of your assets starts to fail, what are the impacts and what are the effects on things like your people, your production, equipment around it, or potentially the environment? Those are the topics we'll look at when we talk about failure mode effect or criticality analysis, but you can define them for yourself if you have other areas that you want to focus on, safety, for example, product quality, things along those lines. They're also linked to failure codes. So if you're using the closing codes in EAM, you can link failure modes directly to those codes, so you get that detailed story of, as I'm starting to identify a problem, this is exactly what happens, this is the functional failure that occurs, and this is the impact effect. My asset has failed, my pump is leaking, it's spilling hazardous fluid onto my shop floor, somebody has slipped and fallen, there's the potential for major impacts to our people around that area. So now we're going to talk a little bit about what you can do with the failure codes related to the conversation that we were having earlier. Now, I'm not an engineer. I will not try and explain this to you. If any of you are math majors, feel free to come up here and help me because I'm not. But the understanding is we're looking at Weibull and Laplacian distributions. What does that mean, right? We're trying to identify whether an asset is becoming more reliable as it ages or less reliable as it ages. It's really a calculation that the closer to zero, the more reliable it's becoming. The farther away from zero, the less reliable it's becoming. So these might look familiar. These curves are very similar to what was discussed yesterday. In fact, these were brought up in a single slide by George, but what we have here is a tale of two pumps. On this far left-hand side, we have one pump that looks like it's becoming more or less unreliable and more reliable. On the right-hand side, we have a flip where it's potentially becoming more reliable based on the hazard function, the probability density. So these reliability curves can tell you if your maintenance activities are making an asset more reliable or less reliable. This is part of the reliability planning and analysis module inside of EAM. These Laplacian curves, these calculations, and ultimately the graphs I'll show momentarily are part of that module, which will help you understand what the mean time between failure based on your problem codes is. So if you have a pump that's failed 6 months ago with the same problem code, you can understand when potentially the next failure is going to be. And we'll look at predicting that as well. Now, the next slide we're going to talk about is the American military's CRO-AMSA method. And I wanted to ask, does anybody here know what CRO-AMSA stands for? Good, because it took a while for me to even remember it, and I have to look at this myself. It's the Army Material System Analysis Activity Model. What this means is it is a way for the American military to identify the regression of reliability so they can predict a failure date. There's going to be two modes that we're going to look at with this. There's going to be the CRO-AMSA method and the IEC regression method. If you have less than 5 failures, the CRO-AMSA method will provide you with a more accurate predicted failure date. If you have more than 5 failures, then the IEC regression is going to provide you with a better failure date. So here's what this looks like. And I'm going to bring this up here momentarily, but I'm going to show you a screenshot of here in a minute. We're going to go into the solution right now, and I'm going to talk a little bit about capturing closing codes, and then we're going to look at how we can run these reports for the reliability calculations. So first and foremost, I want to talk a little bit about closing codes. I'm sure all of you, or hopefully, you're utilizing closing codes in your EAM solution today. And if you're not, you're looking to implement a standardized set of these closing codes. Now, closing codes themselves should be descriptive. but you should have a set of them that would help you understand exactly what the problem is, what the cause was, what the failure was, and then what the solution ultimately is, the actions you need to take place. Now, closing codes you can list here independently and get a huge long list whenever you're closing your work orders. Or you can group them by like groups and create code hierarchies. So within EAM, you can specify a group based on a class so that when you are working on a pump, only failure codes and closing codes related to that pump show up for it. Depending on what you select in your action code, maybe only certain failure codes show up or problem codes show up based on the hierarchy that you specify. So you can really limit what people have to select and reduce the complexity of choosing these closing codes. That's very important because you want your technicians in the field, the people that are closing the work orders, to put in accurate data to help you with some of the calculations we're going to talk about here momentarily. So when we look at what we can do with the closing codes, we'll just look at a work order here real quick. And I know that this has been covered in the previous session as well as Tony's session, but you can see that you have the problem code, failure code, cause code, and action code. You can also surface the additional codes here that we talked about, human oversight, tactical, etc. When you're selecting the codes, you're going to get a list of specific codes here that are available. Now, these are related hierarchically to the one above it, so it's going to limit it. But you want your descriptive fields or descriptive codes as best you can so that people are clear on what they're selecting. So what these codes will ultimately do, and this is where we start to get into the Laplacian calculations, which I'm sorry for throwing so many big words around here, but we're looking at the data that's behind the scene. We're going to look at this crude charge pump that we have here. And this statistical failure data is stored in the back end of the database. We've surfaced it through a grid so that you can see what data is being calculated as part of the reliability and planning and analysis module. You can see that we're calculating the mean time between failure listed here, which is going to be very important if you're trying to identify how often a pump is failing and if you're becoming better at your maintenance activities and strategies. You can also surface this information on the Start Center. Here we have a KPI that's specifically related to it, where if you're looking at mean time between failure data, this can be pulled from the reliability planning and analysis calculations to give you an understanding of which assets are failing more often, which failure codes you're having trouble with, and ultimately what you can do with it. So when we're looking at how we can calculate specifically for these assets, how they're growing reliably, we can look at the reliability calculations. So the charts that we were looking at take that Weibull and Laplacian slope and will provide you with the details inside the system to let you know this asset is actually becoming more reliable as time goes on. So you can see definitively if the strategies that you're putting in place are making your assets more reliable. And you can also identify assets that are less reliable, okay? Now, the reliability growth, which is our CRO-AMSA report, which looks like this, and I'll pull it up momentarily on the screen, you can see that there is, and I'm sorry for this being so small, but you can see that there are dates here related to the next potential failure. So you can actually calculate the next date that this asset's going to fail, and then you can get in front of that failure to prevent it. So by utilizing failure codes from the start, the closing code information on work orders, you can actually predict when a piece of equipment is going to fail. Utilizing this information, you can prevent the failures and ultimately prevent the impact effects that we're going to talk about here with failure mode effect and criticality analysis. So now we're going to talk a little about risk and probability. We're actually going to get into the failure mode effect and criticality analysis. When we talk about failure mode effect analysis, we want to know what is failure mode effect analysis and ultimately what is failure mode effect and criticality analysis. So failure mode effect analysis is understanding what effects a failure has. So if a piece of equipment is failing, it might be in a failure mode. It might have a functional failure where it's only partially failing, such as a pump that's pumping less liquid than it needs to. And that in turn would give you a failure mode. By determining these failure modes, you want to look at what point the asset is experiencing the failure and what does it look like. You first start with your functions, so what's the function of it, and you provide it with a name and a verb. That's what your functional failure is ultimately going to look like. Pump leaking, tank corroded, asset seized, etc. Then you want to assess the severity. So by assessing the severity, you want to look at what the impacts of this failure are. You know, if this pump is not pumping the full amount of liquid, is there really a problem? Maybe not. Maybe it's not severe. Maybe it only happens once in a while. That's the probability associated to it. But you want to assess the severity, and that's where we look at what the effects are, the impacts on people, production, environment, equipment, etc. This will help you assess how severe this functional failure would be, and this is all going to be utilized to generate risk. Then you look at the probability. Will this happen every year, every 4 years? There's a 20% chance of it happening. We can also assign a probability for things, as Tony mentioned in his previous session, an act of God. We have these marked as a black swan event. So what if a hurricane hits your plant in Chicago? Highly unlikely that it's going to do major damage, but it's happened before. When you have these unique events, you can identify what the potential costs are and then what your response is going to be. However minuscule the probability is, there's still a chance that it might happen, so you can assign that. But ultimately, you're looking at how probable a certain failure is going to be in your failure mode effect analysis. Then you assign a detection. How do you identify it? These are the cause codes, these are the symptoms, these are the codes that are associated to it. And all of this is used to calculate risk. So we've talked this entire presentation just to get to the point of discussing risk, because that's one of the most important parts that we're going to mention today in getting to the maintenance maturity levels that we're looking for. Risk is a key part of asset performance management. By calculating the risk through understanding what the failure mode effects are, what the impact effects are, and what the probability are, you can assign a risk priority number to your pieces of equipment inside of EAM that you can then use to calculate the criticality of that asset and then put your maintenance strategies forward based on the risk you've identified. So when we talk a little bit about return of risk, this was also in a previous presentation, and I thought it was a very good example, so I wanted to include it in mine. Let's take, for example, the potential risk for a product that's in a temperature-controlled refrigerator. A very small temperature sensor has failed, and that product is now above temperature. So what are the impact effects related to that, and what are the risks related to that? So as time goes on, the return on risk is very high, but at the start it might be very low. So maybe some of the product's discarded, some of it's remanufactured, perhaps there's a replacement of damaged equipment. There could also be special replacement shipping or refunds or discounts in the short term. So because that asset failed, there's a minimal cost. When we look more into the future, perhaps there's agency audits, production holds, loss of production, loss of future sales to competitors, simply because now you have products that are all of a sudden getting ready to be recalled. There could be class action suits because the products themselves failed. There could be a drop in stock price. There could be brand damage. So the cost itself, which from just a small, tiny sensor, can balloon into something massive. Now, this might be a slight exaggeration or something that's overblown, but in reality, the most minor failure can have a major impact not just on the piece of equipment, but also on your operations and your organization. So when we talk about this in relation to a failure curve, you might have seen this in some other presentations too. This is the potential failure all the way to a functional failure. You might have an observed issue, such as a pump is starting to leak, it's starting to smoke. Then you have another issue where it's starting to vibrate more often. Then you have the last observed issue where you hit it before you hit a functional failure. What happens when you hit these failures is ultimately product quality drops and the cost of production increases. So as you start to identify the functional failures, you look at it from the aspect of what you're producing and how much it's costing you. So there's a cost savings basis that's related to getting in front of these functional failures and preventing them. So we're going to talk a little bit about the relationships when it comes to risk management. We're going to go back into the system here in a moment. But when we're looking at failure modes, we look at the probability, the failure effects, the corrective planning, and then ultimately what we're going to look at is mitigation strategies. Because once you identify these failure modes, you've identified the risk. If this pump is failing, it's leaking, we can't produce as much as we normally would, we're losing money that way, then what can we do to mitigate those effects? So you can identify specific strategies you can put in place, whether they're enhancing and preventive maintenance schedules or process controls, and apply those to ultimately reduce that risk score. So this gives you a way to reduce the risk and ultimately reduce the impacts that you might have if there's a functional failure. Now I do just want to note, this was the same report that we had showed briefly, much larger here, but you can see those IEC expected dates of failure. So you can base that on problem code, failure code, cause code, and action code. So if you want to see specifically when the next failure is going to occur based on one of these problems or one of these cause codes, you can identify that. So I want to draw your attention to the right side of the screen. We have what's listed here as our RCM details. There's 3 risk levels that you can identify. There's risk analysis, there's risk assessment, and there's failure mode effect and criticality analysis. Risk analysis is the most basic one where you can just do a basic risk review of the asset. Risk assessment can take into account other pieces of equipment, but a failure mode effect and criticality analysis is going to look at the failure modes and the impact effects associated to them. Now, I've done a lot of talking about this, but I think it's going to come together when you actually get a chance to see it. So by looking at the risk score that's identified, so I'm going to go back here, you'll notice that there's a risk priority number that's listed here and a risk level, that this hot number is high and that this risk level is unacceptable. So we want to bring the risk of this asset down. Now, what drives that calculation? First and foremost, it's the failure mode effect and criticality analysis that we have here. I'm going to expand all of these. I'm going to show you a few of them. We're looking at the function of this pump. It's to pump 2,520 gallons at 500 gallons per minute. And right now, we have an unacceptable risk that it may not be able to meet that function. One of these functional failures is that the pump capacity itself is too low. This is where we start to identify what the risk is based on the impact effects that we have. So drawing your attention to the items underneath it, we have an impact on the environment. There's spillage or there's emissions, but it's contained, so it's not a major impact effect. You'll note here there's a severity on the right-hand side. There's also severity on the functional side here of the functional failure of a 4. These items are what calculates the risk level. So going through a couple more of these, we look at potentially there's an impact to equipment, where there's moderate damage to the equipment, there's some downtime, but there's spares in inventory, so you're not too worried about it. When you look at production, there's major downtime cost of a day, but the impact is anywhere from $100,000 to $500,000. Can your company stand to accommodate that? Maybe, maybe not, depends on the size and depends on your tolerance for these failures. What I do want to note here is at each stage, for any of these functional failures you want to see on this right-hand side, we have the ability to associate the problem code, the failure code, the cause code, the action code, the symptom, the tactical cause, the human oversight, the workmanship, all the codes we talked about. So you get a direct link to the failure code, the cause codes, and the failure mode itself. So whenever you identify one of these, you can link it back to the failure mode and you can use that for analysis as well. There's also a standard work order. Now I'm assuming everybody here knows what the standard work order is, but I'm going to just explain it very quickly. It is a template that contains your activities and the tasks that you need to complete so that you can reuse it over and over. It's basically a template work order. What's great about this is if you encounter this failure mode, you know exactly what to do to correct it. That's what's in the standard work order, and that's where the linkage that can help benefit you from the start is with failure mode effects criticality analysis. And I'll show you how you can select that here in just a moment. But the calculation itself provides us with that risk priority number by looking at the probability that this is going to fail and the severity. So those two items that are listed here are the calculation. This one is a 15 to 19 range, and that's why it puts us in a high risk level range. If we look at the excessive pressure, this one is probable to happen within the next year, so it's got a high rating in severity. Then it's going to look at the impact effects. So there's major damage to equipment, so those combined are going to provide us with a calculation of 15, which puts us in that range, which puts us at a high level of risk. So this failure mode is optimal to apply mitigation strategies to reduce the risk. Now, you may be asking, do I have to apply these to every piece of equipment or create them one-on-one? No. You can actually create them from other pieces of equipment. So if you've done a failure mode effect and criticality analysis, or by a show of hands, how many of you have reliability engineers in your organization? So your reliability engineers, if they're working EAM, can help input this information, then you can copy it over to other assets. You can also create what we call an RCM template. So by looking at the RCM template, this is where you have detailed information related to the failure mode effect and criticality analysis that can be associated based on class. You can have your RCM information that's here, and then apply that to assets using this template. You can also identify the failure mitigations. So when we have failure mitigations, this is where you can buy down that risk by increasing the PM schedules or adjusting your strategies and apply it to ultimately reduce the risk score and then reduce the risk of failure for that asset. So you can associate these to any pieces of equipment that are part of the same class generally, so you can associate them that way. So we have the ability to copy the RCM information from other pieces of equipment and from the templates. So I want to show you when you actually create a work order, if you've identified the failure mode, all these failure modes are stored directly with that asset because it's related to that RCM tab. So if you identify that the pump capacity is too low and you select this failure mode, it's going to not only apply the standard work order with the tasks and the information that you need to execute the work to prevent that failure mode from getting worse as an observed issue, it's also going to include the problem code, failure code, cause code, and action code, or any of the other closing codes that you associate, which can then be used in the calculations we saw earlier, determining if your assets are becoming more reliable or less reliable based on the strategies you're using or based on the failures you're seeing. Now, when we're looking at mitigating the risk of failure, there is a tab for RCM failure mitigation. Now, this one here, we can look and see what we can do to reduce the risk of excessive discharge pressure. So right now, if we adjust the probability by saying increasing this pump rebuild from every 2 years to every 1 year, that will in turn reduce the risk because the failure that we're seeing is directly related to the amount of time it takes to rebuild the pump or how long we're waiting on it. So by adjusting this schedule, you're going to reduce the risk of failure. In order to do this, we can simply apply the mitigation and save it. Now, that has brought our mitigated probability to low and ultimately reduced our risk level range from the 15 down to a 12. So instead of it being high risk, it's still within a certain range, but it's been brought down based on the failure mitigation we've applied. Now, these failure mitigations don't just have to be adjustments to PM schedules. You can create whatever mitigation types you deem important to your organization for reporting purposes, and then apply those mitigation types here as well. So we've constructed a few here based on process design and process control or equipment modification. This would be design changes to the piece of equipment, or you're implementing condition monitoring. We're actually starting to track the aspects and the measure points and then executing work based on those crossing the thresholds. Now, when you have all this information associated, you can ultimately look at a heat map that's related to it. So if you want to identify which assets in your organization are of the highest risk, you can present yourself with a risk matrix. So by creating a risk project in EAM, you can associate these failure mode effects and criticality analysis to the individual assets and equipment, and then ultimately see which ones are at the highest risk for failure. So you have some here in the upper right-hand corner that will be prime for implementing strategies to reduce the failures that are associated to them, and you can see what the potential failures associated to it would be as well. So in summary, we talked about standardizing failures, standardizing failure codes. These provide the basis for your reporting. So having standardized codes across your organization are going to be very helpful when you're trying to understand if the assets themselves are becoming more reliable, and standardization improves your reporting. We talk about assessing risks. This is where assessments and analysis provide you the understanding of the risks and where to focus on your reductions. So by looking at the failure mode effects and criticality analysis, you can see what the impacts to anything in your organization is, and ultimately how risky not maintaining that piece of equipment is. Finally, you can look at strategizing. By implementing those failure mitigation strategies, you can reduce the risk and ultimately reduce that number, which could then prioritize other pieces of equipment in your organization for more maintenance or maintenance strategies. So by utilizing the tools that you have at your disposal here, not only can you identify the risk, but you can reduce it and then ensure accurate reporting and application to other pieces of equipment within your organization. But it's all based on the standardized closing codes to start with. All right, well, thank you so much. I'll be around if you have any other questions.
Thanks, Dan.
Yeah.